In this video I want us to consider our final little technique for dealing with maybe more complex integrals, and this one's called integration by parts. A super neat little technique, and it's based on an understanding of the product rule. And that's the product rule for differentiation. So let's remember what the product rule says, and we can express it in slightly different ways. I'm going to use u and v, so I'm going to say the derivative with respect to x of u times v is equal to u dv dx plus v du dx. Now hopefully we're all comfortable and happy, familiar with that one there. So let's now integrate both sides of this, and we'll integrate both sides with respect to x. So what we've got then on the left hand side is the integral of d dx of u times v with respect to x, and on the other side, so basically on all of these we're just putting a kind of integral with respect to x around it there. So what's that, a du dx. Now we can't sort of do too much with these on the right hand side, but this one on the left hand side, well, really we're saying we're integrating the derivative of u times v. So if I said what's the integral of the derivative of something, and we're doing both of them with respect to x, well then I've just got that something, haven't I? So on this side it's really just u times v is equal to, write these ones out again, with respect to x, and v times du dx with respect to x. So I'm going to rearrange that now and take this term here and make that the sort of subject of the expression. So I'm going to say the integral of u times dv dx with respect to x is equal to u times v minus the integral of the other one here, so v times du dx. Now, that is our result that we're going to use for integration by parts. And I would suggest to you that at the moment that probably doesn't look particularly useful or particularly straightforward. But what we're going to do is say that if we can get our integral, or our integrand over here, in the form of one function of x times another function of x, then we'll let one of those functions be u, and we'll let the other one be the derivative of v, and then maybe on this side this will actually become a simpler expression. So maybe it'll turn out that when we integrate dv dx to get v, and when we differentiate u to get du dx, that this integral over here will be something that we can deal with, even though the original one wasn't something we could deal with. Now, just before we go on any further, and I should say that probably sounds like you can't get your head around at the moment, which is fine, we'll do an example. But just before we go any further, this formula is on the formula sheet. There it is, that's how it appears. It's straight after the chain rule, product rule, quotient rule. On your formula sheet is then integration by parts, now listed in function notation and also in the UV notation, which I've used just here. So you don't have to remember that, which is great because it is possible to get sort of U's and V's mixed up, but we need to make sure that we know how to use it. Now, just before we go on to do an example, let me make a note about if we're using this for definite integrals. So let's note that for definite integrals, in other words, when we have bounds for our integration, so if I was taking the definite integral of something which I could get in this form here, then the u times v bit I would evaluate, as I usually do, between b and a, and then this second integral here would be also bounds of integration between a and b. So it's just really saying that, you know, we treat this bit as though it's already been integrated, and we do the evaluation between b and a, or, you know, evaluate at b minus its value at a, that sort of thing. So that's not on your formula sheet, but that's fine. It's just got the bounds of the integral there. All right, let's take an example. We'll start with the very first question in 11H. And it's asking us to take the integral of x times e to the negative x dx. Now what we've got in this integrand here is a product of two functions of x that for a start are pretty unrelated. Now if that had been an x squared term, if that was x squared, then this would actually be the derivative of that, wouldn't it? Or the linear would be the derivative of the quadratic. So we might be able to use a substitution technique. But here, there's no way that this is in any way related to the derivative of that. There's no way that x is really related to e to the negative x. There's no trig substitution. There's no partial fraction. So there's really nothing else that we can do here. So it's this situation where we've got a product of two functions of x that we don't seem to be able to relate in any way. That will often be when we can use integration by parts. So because I want on this side to have my integrand in the form u times dv dx, I'm going to pick one of these to be u and the other one to be dv dx. And part of the key normally is to try and pick a u which will become simpler when I differentiate it, because I'm going to have du dx over here, and a v which when I anti-differentiate it, so when I go from expressing this dv dx to v, it doesn't become any more complex, because I don't want this to get any more complex. So I'm going to say let u equal x, and I'm going to let dv dx equal e to the negative x. Now initially that may look a little bit strange, but I'm trying to get it in this form. So I'm just saying I'm going to let dv dx be that, and then I'm going to work out what a v would be so I can place it in those 2 points. So as a result of that then, I can say, well, the derivative of u with respect to x would just be 1, and I could say v is the integral of dv dx. So what's the integral of e to the negative x? Well, it's negative e to the negative x. Now e is kind of a nice straightforward one, isn't it? Because it sort of differentiates and integrates the same way. But notice that I haven't really come up with anything more complex by integrating that. If you're thinking, where's the plus c? Don't worry too much about it, because we'll add the constant of integration right at the end. Let me state my rule again. So I'm saying that if I integrate something of the form u times dv dx, then it's u times v minus the integral of v times du dx. So therefore, the integral of x times e to the negative x, well, now it's just a case of substituting. So that was my u. So on this side, I need u there, and I need the derivative of u in there. I need v here and there. So there's my u. So that's going to go out here. U times v, well, v was negative e to the negative x, minus negative e to the negative x was v, and du dx was just 1. So how does that look now? That's negative x e to the negative x plus the integral. I'll just take those two minuses and combine them to be plus e to the negative x dx. So that's negative x e to the negative x. And the integral of e to the negative x is negative e to the negative x. And this is where I can put my plus c on. You know, there might sort of be constants of integration come out at various points, but we could just combine them all into that single one. And that's the integral there. I guess I could take out a factor of e to the negative x and express it in factorized form. But there we go, an integral using integration by parts. There are various other ways that it can be used where it's not as obvious, and in fact some really neat kind of ones that we can do, like integrating the natural log of x and integrating inverse trig functions. But for this example, we'll just do that one.